For problem 3, we will have a circuit with a battery, voltage V, plus minus. Then we will have a switch. Then we will have a resistor, resistance R. Then a capacitor, capacitance C. And we close the loop. At time moment 0, the capacitor was uncharged. The charge on the plates of the capacitor was 0. We neglect self-inductance. We put L0. We are looking for the charge on the plates of this capacitor as a function of time. We need to find Q as a function of time. Which law will we use? Faraday's law. Integral E dot dr, closed path, is equal to minus d dt of the flux of the magnetic field B dot ds, where ds is area vector. Area is S bounded by this path. And we follow our usual steps. At time moment 0, I close the switch. So this is just a wire now. And I choose the direction of current to be clockwise. Current is leaving positive terminal of the battery. So current is flowing this way. Then reasonable choice of positively charged plate of the capacitor is this choice. Plus Q and minus Q here. Next step, I need to choose the direction in which I go around the loop. And I will go around the loop in the clockwise direction, in the counterclockwise direction, as we always do. You put your right hand, you bend your fingers in counterclockwise direction, and your thumb shows direction of ds, which is out. Area vector ds is out. Now let's look at the right-hand side of Faraday's law, d phi dt. What is d phi dt? d phi dt, phi is integral b dot ds plus minus li if we have inductance, but we neglect inductance. So flux is 0, which makes the right-hand side of Faraday's law 0. Now I need to write the left-hand side of Faraday's law. And let's go around the loop in the counterclockwise direction. And then when we go, we will start with the battery. When we move down, dr is down, we move, there is negative change in voltage, which means positive change in E dot dr. So I put plus V. Then we keep going. From plus to minus, the electric field is down, but dr, we go in counterclockwise direction, dr is up. Electric field is down, dr up, E dot dr is negative, I put minus. Magnitude of E dot dr across the capacitor is Q over C. Then we come to the resistor. Current is flowing to the right, which means that the electric field rho J is to the right, and dr is to the left. E dot dr are anti-parallel. E dot dr is negative. I put minus, and magnitude of E dot dr across the resistor is IR. Now we come back to the battery, and this is equal to 0 since change of magnetic flux is 0. We don't like this equation because we have two unknowns, Q and current. We need to relate them. Current is plus minus dq dt. Which sign do we choose, plus or minus? Current, this current is coming to the positively charged plate of the capacitor. Q increases, derivative of Q is positive since current is coming to the positively charged plate of the capacitor. So we choose plus, dq dt is positive. I is dq dt. And now I bring it into my equation. I have V minus 1 over CQ, and then I have minus R. I is dq dt. and this is equal to 0. Now let's rewrite this equation. I always start with the highest order of the derivative, r dq dt. We bring it to the right, plus 1 over c q, and this is equal to v. This is the equation that describes the charge on the plate of the capacitor as a function of time. We need to solve this equation. If you know how to solve this equation, you use the method that you like. I will use the same method as the textbook uses, which means that I will be looking for the solution of this equation as the sum of two solutions. Look at this. This is first order linear inhomogeneous equation. We have non-zero right-hand side. So I will look at the solution of this equation as sum of two. One is some particular solution that I will choose as steady state. So Q steady state plus Q homogeneous. Homogeneous means that right-hand side is 0. So first of all, let's find Q steady state. For steady state, time derivative is 0, no time-dependent processes. So I have 1 over c q steady state is equal to v, which means that q steady state is equal to c times v. We found q steady state. Now let's find q homogeneous. For q homogeneous, I need to rewrite this equation without the right-hand side. Let's now find q homogeneous. I rewrite this equation with the 0 right-hand side. For q homogeneous, r dq homogeneous dt plus 1 over c q homogeneous, I put h, and this is equal to 0. So this is first order linear homogeneous equation, and as in our previous problems, I will guess the solution for this equation as unknown constant alpha times exponential function to minus, that is crucial, minus beta unknown constant times t. So first of all, I will find beta. How to find beta? I take my guess for q homogeneous and I bring it back into my equation, which means that I have derivative of r, first r still here, then dq homogeneous dt, I need to differentiate this, alpha e to minus beta t, chain rule gives me minus beta. We are done with this guy. Then it is plus 1 over c, q homogeneous, which is alpha e to minus beta t, and this is equal to 0. Let's solve for beta. First, I simplify this equation. I divide both sides by alpha. I divide both sides of this equation by e to minus beta t. And what I have is minus r beta plus 1 over c is equal to 0, which means that beta is equal to 1 over rc. We found beta. Now we know steady state. We know beta for our homogeneous solution. We need to find alpha. How do we find alpha? We find alpha from the initial conditions. But first of all, let's write q as a function of time as steady state plus homogeneous. I will have q as a function of time is steady state. Steady state is CV plus q homogeneous, which is alpha e to minus beta t, minus t, and beta is 1 over rc. Now I'm ready to use my initial condition to find alpha. I have one unknown here, which is alpha. Let's find alpha. To find alpha, let's use our initial conditions that tell us that Q at time moment 0 is, let's look at this formula. It is CV plus alpha, and e to 0 is 1. So it is just plus alpha. And this is equal to 0 from our initial conditions. So what is alpha? Alpha is equal to minus CV. Now we know everything. Let's write our final solution for the charge as a function of time. I will erase this equation and we will write it here. What is Q as a function of time? Q as a function of time is equal to CV plus alpha is minus CV, and then e to minus t over RC. Now I factor out CV. I have 1 minus exponential function to minus t over RC. And this is our charge as a function of time. Now let's find current. What is current as a function of time? Current as a function of time is dq dt plus dq dt, because current is coming to the positively charged plate of the capacitor. I need to differentiate q. Derivative of 1 is 0, then I have minus CV here, and then I differentiate the exponential function minus t over RC, and the chain rule will give me minus 1 over RC. Then I simplified C and C, minus and minus is plus, and we have current as a function of time as V over R times exponential function to minus t over RC. And now let's plot both charge and current. Now let's plot Q as a function of time. Time moment 0, e to 0 is 1. 1 minus 1 is 0, as it should be. At time moment 0, charge was 0. As time tends to infinity, 1 over infinity is 0, so asymptotically it will be approaching CV. Does it make sense? Yes, it does, because look at this. So as time tends to infinity, which means that we wait for a long time, steady state is established. When we have steady state, there will be no current through the capacitor. So this voltage change across this resistor will be 0. And yes, charge on the plates of the capacitor will be just C times V. And now let's plot the current as a function of time. Current as a function of time. Here, before we start our clock, current is 0. And at time moment 0, I looked at current, e to 0 is 1. So all of a sudden, current jumps to V over R. Why does it happen? This change, because we neglected self-inductance. That's why current jumps. But then, time tends to, I'm looking at current. Time tends to infinity, and current tends to 0. As we wait for a long time, there will be no current in this circuit as expected, because the steady state will be reached. And now we see from this formula that as time tends to infinity, 1 over infinity is 0, and current will be 0.